happy that so many of you signed up for these introductory talks. I must say that for students who've taken any of my courses on game theory, today won't be that much new, but I hope that you'll get excited also about the topics of my colleagues who will follow up in the upcoming weeks. So let's get started right away. So this is the fourth Studium Generale lecture series on game theory. We had 3 before, and that's also because we do have quite a number of staff working on game theory here at UM. I would say it's around 40 to 50 people if I include also the PhD students. And this not small community led us also to organize the so-called World Congress of the Game Theory Society. These are congresses that take place once every 4 years. And well, the fact that we were allowed to organize it here in Maastricht also shows that there's quite some experience around. So this is, by the way, this is a small picture of the event in 2016 when we also had a few Nobel laureates in economics presenting their work or commenting on other works here at Maastricht University. For tonight, I want to give you kind of an easy introduction into many different areas of the field. So I'll cover quite a number of very basic topics, but I'd like to end also with a slide with some slides and comments on more recent work. We'll also look into applications of game theory because, as Rob already said in the introduction, game theory is nowadays applied in many different areas. It really started off as game theory, and for many decades, one couldn't find many examples of applications of the field, but this is appearing more and more. So you'll also see some of that in the upcoming talks in the next weeks. For tonight, I'm really going back to basics and back to the early days. And I've listed 4 of my heroes here. And I think that some of these names may be familiar to you. John von Neumann, John Nash, Lloyd Shapley, Bob Aumann. Maybe the first one's most famous, John von Neumann, because he's one of the let's say most influential mathematicians of the last century. Our modern computer, we in a way also have to thank him for that, because like Alan Turing was working on building computers and computing devices, I should say, in England, and John von Neumann was doing this in the US in the first half of the previous century. Then we have John Nash, whom you may know from this movie, Beautiful Mind. And then I guess the other 2 names are a bit less familiar, but all these people are connected, not just to each other, but in a way also a little bit to me. So they all got a Nobel Prize. You see here in what years they got it. And they also got this so-called JVNT Prize, which is the John von Neumann Theory Prize. So they're all connected to John von Neumann. They're all mathematicians. There's no Nobel Prize for mathematics, but there is something similar for operations research, which is a subfield of mathematics, where, let's say, decision problems are being examined. This John von Neumann Theory Prize has the flavor of being something like a Nobel Prize for operations research. Now, all these people are mathematicians, and I'm too. So I will confront you with a few equations here or there. Don't worry too much about it. If you understand, it's fine. If you don't understand, I'll try to give you the interpretation as well. At the end, I want to kind of give you also my story, how my story relates to these people and how my work relates to these people and how it led to more recent activities in the field of so-called evolutionary game theory. But let's start with basics. And for me, it starts with a very small, simple model introduced by John von Neumann in 1928. Basically, he was still very young at the time when he wrote this paper. And the idea was that if people are somehow involved in a conflict, then usually they have different plans of how to approach the conflict. So let's say that we have two players or two parties involved in this conflict, and the first player, that corresponds to the rows of this, let's say, matrix, and the second player corresponds to the columns. So suppose that the row player has 4 different plans of actions, and the column player has 7 different plans of actions. Then theoretically, we could consider what's happening if a row player chooses the 3rd plan and column player chooses the 7th plan. Then we see there's a 5 in this entry in the 3rd row and the 7th column. And this is interpreted as the row player wins 5 from the column player. Now, what this 5 means is completely up to the type of problem that you're looking at. It can be money, so it can be €5. It can also be, let's say, things like market shares, so you get 5 more shares or something like that. And there's also all kind of different interpretations possible. But let's say, suppose that you understand everything you try to oversee what's happening in all these cases, and you know exactly also what plans your opponent might be doing, then still, so you could write down all these possibilities in this matrix, and then still you wonder, like, what should I do? What's the best option for me? And this is exactly the problem that John von Neumann was addressing in this very early paper. And to explain to you what he discovered, let me start with a slightly more simple game. So suppose there's just 2 actions for each player. The players here are parties, so I'm not talking about parlor games. A game is just some kind of conflict where you have multiple parties who can do multiple things, and you want to know what's best. So if player 1 is facing this problem, you could say, well, he should be happy because he's always getting something. So either he's getting 1 or 3 in the first row, or he's getting 4 or 2, based on the choice of player 2 in the second row. Maybe he thinks, well, let me choose the second row because then I at least get 2. Player 2 is the guy who has to pay. So player 2 could consider something like, let me choose the right column, because if I choose the right column, I never need to pay more than 3. So if they do it like that, player 1 would choose the bottom row and player 2 would choose the right column, and player 1 would find himself getting 2. And if we assume that they play this game repeatedly, player 1's always getting 2. And player 2 is kind of happy because he was expecting maybe I have to pay 3, but it always happens that he's paying 2. Now, as soon as player 1 starts noticing something like that, he thinks, well, if he's always playing the right column, maybe it's better for me to choose the top row. Now, of course, you understand that if player 1 would be starting to play the top row, player 2 might consider choosing the left column. So this is kind of a runaway argument, and it doesn't lead anywhere. So what von Neumann tried to do is saying, well, maybe we should be less predictable, and maybe we should use some probability device to hide our choices. So suppose I'm choosing the top row with some probability and I choose the bottom row with some probability. And of course, these probabilities have to add up to 1. Then I would get something, an expected payoff in the left column. So expected payoff, you can interpret it as this would be the average payoff if I'm playing the left column repeatedly and player one's using 1 minus pp as probabilities. Because with probability 1 minus p, he gets 1. With probability p, he gets 4. And altogether, this summarizes as 1 minus p plus 4p, which is 1 plus 3p. Now, for the right column, this expected payoff would be 3 minus p. And if player one is looking at that and thinks, well, suppose I want to maximize the minimum of these two numbers, 1 plus 3p and 3 minus p, then I'm actually looking at two graphs, one graph being 1 plus 3p and one graph being 3 minus p. And I want to look at the minimum of these two things and find the maximum, which you see right here in the middle. So player one thinks, if I just flip a coin, then in the first column, in the left column, I get 1 and 4 each half of the time. So on average, I get 2.5. And if my opponent is playing the right column, it's half of 3 plus half of 2, which is also 2.5. So no matter what my opponent is doing, I know for sure I'll get at least 2.5. Now, of course, player 2, the column player, can do something similar, but he's just looking at how much do I have to pay. So if player 1 chooses the first row, I have to pay 1 plus 2q. If he chooses the second row, I have to pay 4 minus 2q. I would like to minimize the maximum. And surprisingly, and I think this was really surprisingly also to John von Neumann, this maximum in the one problem and the minimum in the other problem are exactly the same. And this is not just a coincidence for this particular matrix, but von Neumann showed that no matter what matrix you take, if you look at the minimum over all columns, so player one is looking, what's the worst expected payoff I can get based on the probabilities that I'm using. If player one maximizes the minimum over all columns, the number he finds is exactly the same as the number that player two finds when he minimizes the maximum over all rows. So player one maximizes the lowest possible payoff he can get. Player two minimizes the highest possible payoff he has to pay. And they arrive at exactly the same number. And this number is called the value of the game. So for the previous game, we would have that 2.5 is the value of the game. And the strategies involved would be optimal strategies. You can also interpret this value as the number that would make it fair. So if you want to make the game fair, because like the way the numbers are written now, player one on average would be able to get 2.5 out of this game. So you might as well say, well, I'm not going to play the game with you because I'm always paying if I'm player two. So I'm only willing to play the game to player one if he first pays me 2.5. So it's like, what's the price of the game where we both have equal chances in winning or losing? So this fact that you have a matrix and maximizing it from one way and maximizing the minimum over the columns and minimizing the maximum over the rows, this is a more general phenomenon that was later established for a slightly more general class of optimization problems. And this led to the field of so-called linear programming, which is really at the heart of what's known as operations research. And you may not know it, but operations research is used all around you because it's largely used in all kind of planning and scheduling problems. So in routing things, in ordering things, in planning processes, in all kind of manufacturing systems, it's all based on this type of structure. And John von Neumann kind of started all this field. Now, in the 40s, John von Neumann teamed up with an economist, Oscar Morgenstern, and they wrote a book on all kind of models of economic behavior. Economic behavior essentially is all conflict because people are competing and they're competing in the market. And the idea was that if you want to advise companies in how to behave in a market, then maybe you should first understand basic principles of how this competition works. And basic principles means examining small matrix problems like the one I gave you. And of course, there are many other examples of basic problems. So tonight, I'm going to show you some of these basic kind of decision problems or principles of sharing money, where you'd also like to know what would be a fair way of doing things. So 1928, John von Neumann was looking at games where there was only two parties involved and one party had to pay the other party. So there's no possibility like how to deal with three players or what if they both get money. And that exactly takes me to John Nash, because that's the problem that John Nash addressed when he arrived at Princeton and started working on a PhD thesis on this type of decision problems, where there's not just two players, but there can be n players, where n is just some natural number. So it could be 17 or 64 or 213, any number you like. Now, remember that suppose, like here, I still visualize just a two-player game where the row player gets the black payoffs and the column player would get the orange payoffs. You see it's no longer a zero-sum game, because if I write the payoffs for the column player explicitly, we see that the numbers don't add up to zero, which means that sometimes they both get money, like top left or bottom right. Sometimes one is winning and the other one's losing, like top right. But if you would imagine a three-player game where the third player would also have two actions, we would have to visualize, let's say, a cube where there's two of these matrices, where the third player is deciding which of these matrices to play. And every entry would have three numbers, one for player one, one for player two, one for player three. So if we move into 17 players, we would be looking at a 17-dimensional cube. Okay. John Nash worked on this type of problem, no matter how many players you would take, as long as it's a finite number. So we could even be playing a game with all you guys. And if I look at my screen, I think there's now 150 people here. So this would be a 150-dimensional problem. And John Nash knows that there will be a solution. So how does he know that? So what's the solution? Maybe we should start with what's the solution. As you probably recognize, the black numbers are still the same as in the game that we looked with von Neumann. It's just the same numbers. So role player thinks, I know this game. I just flip a coin. I always get 2.5. Well, maybe that's not too clever, because if column player is looking at these numbers and anticipates that the role player is kind of silly and just flips coins, then he sees that if he chooses the left column, on average he would get 3. While if he picks the right column, he just gets 0.5. Clearly, left column is much better for column player than the right column. However, if the players are playing this game repeatedly and column player is always choosing the left column, then player one starts to scratch his head and wonder, why am I flipping coins? I'm getting 1 and 4, but I could get 4 all the time by just playing bottom. And again, we would arrive in a runaway argument. So that doesn't really lead to something stable that we could call, that's a nice solution. Instead, it would be good if role player looks at the payoffs of his opponent and thinks, if I do 1/3, 2/3, my opponent gets 2 on average if he chooses the left column. He gets 2 on average if he chooses the right column, because -4 times 1/3 plus 5 times 2/3, that's 8. That's 6/3, which is 2, right? So if he does 1/3, 2/3, well, then his opponent, column player, is indifferent in what to do. And column player could just play this 1/4, 3/4, and by doing so, he can make sure that the row player just gets 2.5 in the first row and 2.5 in the second row. So this pair of strategies that I now outlined is what John Nash calls an equilibrium for the game. It's a solution where none of the players has any better alternative. If player one plays 1/3, 2/3, player two can play left or right. It doesn't change his payoff. He will always get 2. Row player can do anything different, but it doesn't change his payoff. And it doesn't change, maybe that's not that important, but what's more important, he cannot get anything better. So even in hindsight, if they would look back at the game and think, what have we done? Well, they could only conclude, I've done my best. I couldn't have gained anything more. And that's what's characterizing this famous equilibrium concept that John Nash introduced. And John Nash showed that such an equilibrium exists no matter how big and in what many dimensions you build your matrix. So even if we have a matrix with 150 dimensions and we have 150 numbers in every entry, then still each of us would be able to choose a probability distribution over our actions, and none of us would be able to improve if we were the only ones changing strategy. And so this existence result, that's what John Nash is famous for. And actually, this is his paper in which he proves it. It's a 1-page paper. So I always tell my students that if you want to get a Nobel Prize, you just need to write 1 good page. That's all it takes. And if you ask me, is this difficult? And well, maybe it's difficult for some of you, but I can tell you that any student who is doing an undergraduate program in mathematics will understand every line that's written on this page. So no, it's not that technical. It's just a very sharp find, a very nice result, a very good observation that triggered this proof. And by the way, in the bottom he says, John Nash says that he's indebted to Dr. David Gale for suggesting the use of some theorem that he was applying. We'll see this David Gale slightly later in the slides as well. So he wrote the proof in 1949. He got the Nobel Prize in 1994, basically for his pioneering work on equilibria. And as you see, it says for their pioneering analysis. Well, it's because he had to share the prize with 2 other people, Reinhard Selten and John Harsanyi. And those people have spent all their life on what's known as equilibrium refinement, because as the title of this slide says, it says equilibria, which is multiple. So unfortunately, John Nash's solution, well, he shows there's at least one, but in most cases, there are many, for there are multiple. And if there are multiple solutions which have different payoffs to the different players or different effects for the different players, then often you would still not know which one to play. So what people have been trying to find for many years, but not in a successful way, is a solution concept that would find you a unique solution, no matter what numbers are written. Because if you have a unique solution, you always know exactly what to do. If there's multiple solutions, you have a choice. If you have a choice, and the choice also has different effects, what to do? It's still an open problem. But the field of game theory is young, so there's options for many to continue in this area. John Nash became famous a few years later, 1998, because this science author, Sylvia Nassar, wrote a book on his life, and the book is titled The Beautiful Mind. And a movie was made out of it a few years later with Russell Crowe acting as John Nash. Now, I don't want to try sharing movie with sound online, so I'll add a link in the PDF that I send around afterwards. So if you want to watch a short fragment of this movie, in which I would say the director of the movie is trying to show some game theory, just have a look. So I singled out the argument where I think the movie tries to show what Nash means with an equilibrium. But to be honest, they fail because the solution they show is not an equilibrium. But it's up to you to see if you understood what I said before and to find why it's not an equilibrium. In the booklet, I saw there's also something written on prisoner's dilemma. Now, prisoner's dilemma is the kind of game that you see outlined in this matrix bottom here. So the blue numbers are for the row player, the orange numbers are for the column player. You see 0 is bigger than -1 and -5 is bigger than -10. Therefore, for a row player, it's always better to play bottom. And for column player, it's always better to play right, which means that they would always arrive at the most, well, at the solution that's giving each of these players -5. So, which can be interpreted as 5 years imprisonment. Now, they both get -5, and if they'd be clever, they would cooperate and both get -1 only. However, this C action against the C action, it's not an equilibrium, because as soon as you know that your opponent is doing C, you would like to do D. And in the movies that are attached to this slide, you can see some nice modern day examples of prisoner's dilemma, where players would like to do C, but there's a strategy that's always better. And so I would say movie 1 and movie 2 are nice introductions so that you get a flavor for what's happening if players are trying to choose these things simultaneously. I would also suggest to also watch the third movie, because there one of the players is taking a very original approach in trying to establish a fine outcome for both. Now, back to this book that Sylvia Nassar wrote on John Nash's life in 1998. If you look at the contents of this book, there's a chapter titled Lloyd. And it says Princeton, 1950. Now, Lloyd in Princeton in 1950. Who's that? Well, that's Lloyd Shapley. That's next person on my list. Who's Lloyd Shapley? Well, Lloyd Shapley was interviewed because he was a fellow student of John Nash. Actually, they've been sharing a dormitory in Princeton in the early 50s. And when Lloyd Shapley was interviewed on describing Nash, he said that John Nash had this logical, beautiful mind. And that's what led to the title of the book. Well, it's not just that Lloyd Shapley gave the title for the book, but Lloyd Shapley was also working on games. And in Princeton, despite this remarkable result that Nash derived, Shapley was seen as the upcoming star working in Princeton, and the community was von Neumann. So von Neumann thought that Shapley was a very, very good. And why is that? Well, Shapley came in with some fame. So when Shapley arrived in Princeton, Lloyd Shapley is the son of Harlow Shapley. Harlow Shapley is a famous astronomer. He was one of the founding fathers of the National Science Foundation of America, and he was the director of the Harvard Observatory. So he was doing quite a lot of famous work in astronomy, and one of the things that, let's say, touches us all is that Harlow Shapley is the person who discovered the position of our sun in our solar system, i.e. in the Milky Way. So before that, many people thought that we would be somewhere central in this Milky Way, but we're not. We're just an insignificant planet somewhere along one of these arms. So, but Lloyd Shapley himself also arrived with some fame, because while he was an undergraduate student, he was drafted in the army and had to serve in China. And while in China, he was breaking Russian weather codes. And for that, he got decorated by a so-called Bronze Star. So he arrived as a war hero in Princeton. And unfortunately, John Nash didn't have all these fancy prizes and fancy family members. So there was a little bit of competition among the two gentlemen. Lloyd Shapley also got a prize. He also got the Nobel Prize. For Lloyd Shapley, it lasted till 2012. And he got the prize for, you could say, the art of matchmaking. He had to share the prize with Alvin Roth, because Alvin Roth worked out a way of, let's say, using an algorithm that Shapley developed in the early 60s for matching boys and girls. Alvin Roth used it for matching organs for donation purposes. So this is the paper that they basically used for getting Shapley the Nobel Prize. And this paper was written by Shapley together with David Gill, the same David Gill that was helping John Nash. Why is that? Well, because David Gill was teaching the game theory course in Princeton. And this paper that Shapley got the Nobel Prize for is titled College Admissions and the Stability of Marriage. Now, these marriage problems, and also the kidney problems, or the organ donation problems, will be explained in more detail in lecture 4 of this series by Monica Salvioli. So I won't say anything more about that. But marriage problems is a bit more than that we're going to open up emotionally about what's happening in our lives. So Lloyd Shapley did many things. And in the early 50s, like I said, he was a fellow student of John Nash. So Lloyd Shapley was also working on his thesis. And in a way, we saw John von Neumann had a value for two-person games. Then we had John Nash with an equilibrium solution for n-person games. And at the same time, Shapley was working on a value for n-person games. So what's the value for n-person games? And how does it relate to the other stuff? Well, actually, it doesn't relate very much to the things we touched before. So this is now something completely different. This Shapley value that was introduced in the early 50s, for a long time, it wasn't much used. There were very rare applications of the theory and of this value. But in recent years, so let's say the last 10 years, machine learning community is catching up, and Shapley value is now quite popular in the machine learning world, where it's used to decide in all kind of feature selection processes. How much weight should we give to different features if we want to train some network to decide things based on large data sets? So I'm not going to tell you about machine learning. I'm just going to stick to the basics here. I'll tell you what's a cooperative game. And again, so here I give you just a 3-player example, but what Lloyd Shapley did was for n players. So where n can again be any number, like the 150 that we are together. So cooperative games are called cooperative games because it's about a group of players that have cooperated. So this example that I show you here is a group of 3 players that we call A, B, and C. They've decided someday that they're going to cooperate for some joint project. So together, they made some money. They got 14. So try to remember. So cooperative game is not about with whom shall I start to cooperate. No, cooperative game, the decision of cooperation was made before. We did work together. We made money. We got 14. And now we look back at how life could have been if we would have chosen differently. So A would say, if I worked alone, I could have obtained 6 on my own. B and C could each have obtained 7 on their own. If A and B had cooperated together, the 2 of them could have made 9. A and C could have made 11. B and C could have made 11. But all these things didn't happen. The only thing that happened is that A, B, and C together made 14. Now they have to decide on how to split the money. A should get a share, B should get a share, and C should get a share. And they want to share the 14 units, which can be 14,000 or 14 euros or 14 million, whatever you like. But they want to share this number 14 in a fair way. Fair with respect to the other numbers in this table, where maybe this sign that you see between S and A, that's the sign for an empty set. So if there's no people cooperating, the value of the coalition, V of S, is 0. So you could say, well, it would be reasonable if A says, well, I want to have at least 6. So I visualize that now in a triangle, where this triangle is basically all possible divisions of 14 among 3 people. I can give everything to A, that's bottom left. I can give everything to B, that's bottom right. I can give everything to C, that's middle top. So if A says, I want to have at least 6, we're on the left side of this blue line. If B says, I want to have at least 7, because I could get 7 on my own, we want to be on the right side of this second blue line. And if C says I want to have at least 7, well, we should be in the upper half of this triangle, right? Well, clearly, if that's all what they all want, then there's no solution, because the intersection of all these half spaces indicated by the lines and the arrows is empty. I can still add what the two-player coalitions want. So this green line, for example, corresponds to B and C wanting to have at least 11. If B and C take at least 11, it would mean that A gets at most 3. However, adding these green lines doesn't make the set more, or doesn't make it less empty, right? It's empty all the way. So there's no solution in this case, but had there been solutions in the intersection of all these blue and green half spaces, we would call that set the core. Now this core is going to be illustrated also by examples in the lecture next week by Marieke Musegaas. So what Shapley did is saying, maybe we should simply look at some fairness principles. What do we want? Well, we would like that the solution, how to split the money, is taken anonymously. If I change the names of two players, if I change the names, but all the numbers stay the same, then the solution should now give the amount to the other player, right? So the solution should not depend on the name of the player. Efficiency means if we have 14 to split among 3 people, we just split 14. We can't split 15 because that's more easy. We can't split 12 because it's more easy, because then there'd be, it wouldn't match with the number 14 that we have. What to do with the remainder? Then there's this property of additivity. If these 3 friends have been in 2 different projects simultaneously, and they made different profits on these different projects, we would like that if we solve each of these problems separately, and we add the 2 solutions, we get exactly the same number as when we would add all the numbers of these 2 tables and then split it as just one problem. So that's called additivity. And then there's this so-called dummy property, which I think also comes quite natural to most of you. I mean, everyone will have experienced cooperation with a group of people and noticing that there's one person in the group that's not really contributing to anything. He's just sitting there, or she's just sitting there, doing nothing. So dummy property says, if you have someone like that in your group, that person should not be sharing in your profits, because this person didn't contribute to your profits. And also, if together you made a loss, well, that person didn't contribute to the loss. So that person should just go home with their own amount of money, or with his own amount of money, and should not participate in any profits or losses. Okay? And what Shapley showed, and that's really a remarkable mathematical feat, no matter how many people you have, if you have n players and you find all these things very natural and nice and fair, then there's just one way of splitting the money. And not only does Shapley prove that there's just one way of doing this, he also says how you can calculate it. It's just the average of what's called the marginal contributions. I'll give you an example so you understand what I mean. So here's the game that we've seen before. Marginal contributions assumes that when these people start cooperating, they not just join all at once, but they join in a sequence. So maybe we first start with A, so A takes the initiative, B joins in, and then C joins in. And what we do is, whenever a person joins the coalition, we give the person joining the amount that he contributes to how the value of the coalition is growing. So here's an example. If we start with A, we go from 0 to 6 because we go from an empty set to a set where there's just one person. So A gets 6 because that's his contribution. Then B joins in, so we go from 6 to 9 and B gets 3. Finally, C joins in, so we go from 9 to 14 and C gets 5. If we take a different order, like we start with B, then B gets 7 because that's how much B contributes to the coalition. C joins in, so C gets 4, the difference between 11 and 7. And finally, A joins in, so A gets 3. We do this for all possible orders. And with 3 players, there are 6 possible orders. So we fill out the full table and we calculate the average. And the average is what we call these days the Shapley value. It says something about what player contributed most to achieving the 14. And in this game, it's player C. Okay? So no matter how you fill your table, no matter how many players you put in your table, there's always just a unique solution. You just carry out this algorithm and you find it. Okay, so that's different from the core, because with the core, sometimes we have no solutions, sometimes we have a full set of solutions. And if we have a full set of solutions, we don't know what to do. The Shapley value, I should say, is well motivated because of these 4 fairness principles. And the fact that these 4 fairness principles determine exactly one unique solution means that if you find other things fair that are not listed yet, then chances are high that if I add this fairness principle as well, there would be no solution. Because here's an example. So David Schmeidler introduced something that we call the nucleolus of the game. So the nucleolus is based on a different fairness principle. So here's the story. We start again with the same situation. We see that all these parties, A, B, C, AB, AC, and BC, they all have their claims. The one-person parties have claims being on the left or the right or the top side of one of the blue lines. The 2-player parties have claims that say, we want to be on this side of the green line. And what Schmeidler actually says is, well, the problem is not so much that we don't know how to share the 14, but the problem is that all these parties are claiming too much. We should just reduce their claims. Everyone has to give in a little bit, right? We can't all get what we want. So we want all parties to give in something on their claims. And what Schmeidler says, all parties should give in the same amount. So we're going to reduce the claims of all these parties by the same number X. Now, some of you may already say, well, maybe 2-player parties should not just give in X, they should give in 2X. Well, that's also possible. That's, again, a different way of looking at fairness, but that's not nucleolus, that's like something called weighted nucleolus. So let's just look at this nucleolus thing. So we're going to make all parties reduce their claims. Of course, ABC is not being reduced because that's what we want to divide, okay? So we're reducing the claims, and then as we reduce these claims, we find that there's suddenly a unique point that's on the right side of all the blue and green lines. And this solution, in this case, it's accidentally, it's a unique point immediately. We call this point the nucleolus. So what could have happened, of course, is that if these lines are moving back, that suddenly we have a whole interval of points that are suddenly available. What we would then do is squeeze in the other lines again until we have a unique solution. So we're playing around with reducing or increasing claims of parties until the solution is unique. But we try to treat all parties equal, where we only move the lines of those that can move without making the set empty. Okay, so this is called nucleolus. And this is a different solution, so it's different from the Shapley value that we calculated earlier. And because it's different, it means it doesn't satisfy the properties of the Shapley value. And so you've now seen different principles of fairness, which means that if you're involved in a conflict and you have to share something in a fair way, you have to consider what fairness principles do you find most appealing. And different nations, different religions, different societies, they have completely different principles of fairness. And what I'm going to do next is to show you and introduce you to different fairness principles that we don't understand in our society because it's not familiar to us, and that people didn't understand in our world for many centuries. So I'm going to take you to my next hero, which is Bob Aumann, as you see, also getting a Nobel Prize in 2005. And he didn't get the Nobel Prize for the topic that I'm going to talk about. So Bob Aumann was the PhD advisor of this Schmeidler that I just that introduced this nucleolus. But some of his work is very nicely connected to the nucleolus, and it's the most fantastic story I know in game theory. And it's a story that I think that everyone can understand. And it's a story that dates back 2000 years. So I really want to bring this story to you. So he got the prize in 2005. He didn't get the prize for the story I'm about to tell you, but he did a lot of work also with people like Shapley working on so-called non-atomic games. What's a non-atomic game? It's a game with a continuum of player. So they're not finitely many, there are uncountably many players in the game. Then of course game is a different story. He also did a lot of work on repeated games. So we're playing the same thing, the same game over and over again. Well, that may be boring. So he was working on repeated game with incomplete information. So very often, of course, in conflicts, we know what we want ourselves, but we have no clue what the opponent wants. We don't know all actions possible. And the fact that we would know all the numbers like I gave you in this very first matrix on the first page, that would be rather rare. So Bob Aumann was working largely on repeated games with incomplete information, where you learn gradually what the game is like while you're playing. Now, those games are a bit too technical for an introductory talk like I'm doing today. So I just tell you that game theory touches on very many diverse areas, and they also touch on war and peace, which was the title of Bob Aumann's Nobel Prize lecture, because war is the most extreme way of conflict and peace is the most extreme way of cooperation. And everything in between is game theory. So yes, we're touching in many different fields. And I'm now taking you to a game that derived from the Talmud, because Barry O'Neill came across this story in the Talmud. The Talmud is like the Jewish book of law around the year 0. So it's a book with many examples on how to solve conflicts. And Barry O'Neill came across a very fascinating story about 3 widows that were all married to one and the same man, and the guy died. And then these widows are going to quarrel because one was married much longer period than the other one. One invested more than the other one. And the Talmud explains how to solve the division problem, how to divide the estate among the 3 widows. So it's a very useful book, this Talmud. So here's the story in an English translation from 1935. So if a man who was married to 3 wives died, and the claim of one woman is 100,000 euro, the second woman wants 200,000 euro, and the third one wants 300,000 euro, but the bank account only shows 100,000 euro, then the sum is divided equally. All women are getting exactly the same amount, 33 and a third. If the estate, so if the bank account has 200,000 euros, then the one who claims 100 gets 50. The ones who claim 200 and 300 each get 75. And if there's 300 in the bank account, then the one claiming 100 gets 50, the second one gets 100, and the third one gets 150. So these are the numbers. We see the claims of the widows on the left-hand side. We see the bank account number in the top row, 100, 200, 300. And in the columns, we then see how the amount is split across the women. So we see something called equal division in the left column. We see proportional division in the right column. We see 50, 75, 75 in the middle column. And for many centuries, people were thinking, that's weird. Maybe something's wrong there. Maybe someone made a mistake. Of course, books were not written in print. They were copied by hand. And actually, there are many things that document that around the years 900, 1000, people were discussing that something must have been going wrong there in transcribing all these numbers. And there's a very intriguing statement at the end of this so-called Mishnah. So Mishnah is one of these stories in the Talmud. So it says that similarly, if it's about any other amount, well, you just share it in the same way. Sharing in the same way? Wow, how's that? How do we share 400? What if there's 4 women rather than 3? So people have been confused for many centuries because no one understood how to do that. And then Aumann and Maschler read this paper by Barry O'Neill, and they started looking into it. Both of them are affiliated with the Hebrew University in Jerusalem. Bob Aumann is quite strict Jewish, so they read the scriptures, they read the books, they want to understand what's happening here, and they figured it out. So here's the solution that they came across. They wrote the Talmud problem as a cooperative game. It's about sharing money, and which means we have to fill a table. And for the 200 case, so that's why you see 200 is red at the top line. For the 200 case, they said, well, we have to fill in these numbers. They want to split 200. So at ABC we write 200, what numbers do we write at the other coalitions? Let's write the amount that remains when we first have to pay the other players. So you see that with BC, there's the number 100. Why is there 100 there? Well, if you look at coalition BC, they would first have to pay A. A claims she should get 100. So let's first give 100 to A. We have 200 available, give 100 to A. How much is left? 100. So BC says, well, we should get at least 100. If I look at any of the other coalitions, like B or AB, if I look at AB, they first have to pay C. Well, if you only have 200, all money is gone. Because you can't spend more than what's available. So C may want 300. If there's only 200 available, C only gets 200. Okay, but nothing is left for AB. So that's why you see zeros in this table everywhere else except for BC and for ABC. If we go to the 100 problem, of course, every party claims at least 100. So if you have to pay someone else, there's nothing left. So there's all zeros. And for the 300 case, BC would first have to pay A. So there's 200 left. AC would first have to pay B. So there's 100 left. And everything else, no money left. Then, if you look at the nucleolus solutions for these games, something surprising happens. So here's the solution for the 100 column. If you see, and this is also what you understand, like if you look at the table, you see A, B, C together, they can make 100. Any smaller coalition only gets 0. So all players are symmetric. And we would expect that all players get exactly the same amount. If we do this nucleolus thing, we could say, well, initially when we start, the core, actually every solution in this triangle is a core solution. So if we have too many solutions, we just raise the claims of all parties simultaneously. And if we raise these claims, we arrive at the nucleolus. If we look at the 200 case, we have the lines for the one-player coalitions. We have the line for the two-player coalition. For the two-player coalition BC. If we raise the claims of these coalitions, we arrive at a situation where the blue and the green line overlap. So the core, I hope you can see my mouse. So the core is exactly the point between the intersections of these 2 points right now. So this little line segment. If I would push the blue and the green line further, core would be non-empty. So I freeze the 2 lines that are overlapping, and I continue pushing the other 2 lines until I have a unique solution, which is the nucleolus of the game. It's exactly the numbers from the Talmud. If I do the same thing for the 300 case, freeze and continue, we arrive again at a unique solution. So what the Talmud simply says, well, if you want to know how to divide the money, just calculate the nucleolus. That's all you need to do. However, if you'd have to do this for a problem where they'd have to split 400, well, we could still get it done with a triangle like that. But if there's 4 widows, we would already not be able to do it in a plane. We would need to have a 3-dimensional picture. If we move to 5 widows, 3-dimensional is not enough. We would need 4-dimensional space to look in, and that's quite confusing. So this is still quite hard. So Aumann and Maschler started exploring Well, that's kind of fascinating. How did they do these things 2000 years ago? And they started looking the Talmud in more detail, and they came across a different story. And this story turns out to be the explanation of the numbers in the other story, because it touches on a very fundamental principle in games. And this principle is what we now call consistency. So the story in the Talmud is that two are holding a garment, and let's say a piece of cloth. One wants to have it all, the other claims half. Talmud says, well, then one gets 3/4 and the other gets 1/4. So here's the cloth. One wants to have it all, the other wants to have half. So you split there. Why there? Well, because that's the part they're fighting over. If two players both want to have the same thing, well, just cut it in two. And I guess that most of you know the biblical story of King Solomon, confronted with two women who both claimed that a certain child was theirs. And then Solomon says, well, if they both claim to be the mother, then we'll just cut it in two, and each gets half, thereby disclosing who's the real mother, who doesn't want that, of course. But you see, it touches back on very basic principles. If two parties want to have the same thing, just split even. Okay? So if we now take a closer look at these numbers, if these two widows, so all three widows went to the judge says, okay, Lady A, you get 50, Lady B, you get 75, and Lady C, you also get 75. So they go home. Lady C says, okay, I got 75, I go shopping. So A and B are walking home together. One got 50, the other got 75. Together, they got 125. If you look at this number 125 and you consider this garment, one claims she wants 100. The second claims she wants to have 200. So if I look at this 125, one says, I want to have 100. The other says, I want to have it all. So the part they're fighting over is 100. They split even. So the first one gets 50, the second one gets 50, plus the 25 that the first one doesn't need. If you look at these two women walking home, together they got 250, but the first one only needs 200. So let's give the 50 already to the third one who wants all. So they split the 200 that they both want. The first one gets 100, the second one gets 150. No matter which women you take, together they got 66 2/3. Each of them wants to have more. So they should split even. So this, if you find this garment solution fair for two players, then there's just one way how you can write the numbers such that for any subset of players, splitting the amount is fair according to this garment. So the way that the Talmud shows this solves this problem for three widows is the only way that's consistent with the two-player solution for any subset of two players. Still, if we have to split 400 or to decide on what to do if there are four widows, it's still quite a puzzle to get the right numbers. But Science always makes progress. So in 1985, Bob Aumann and Michael Maschler wrote a very lengthy technical paper showing that if you find this contested garment fair, then no matter how many people you have, and you have to split some amount of money, and there's not enough to give everything what they want, give every player what they really want. So it's a bankruptcy problem. Aumann and Maschler showed if you find this two-player principle fair, there's just one way of extending the solution to an n-player situation, where for every two-player subset, you would not consider reshuffling the money, okay? Because that would be weird. These women would argue, well, if the third lady hadn't been there, we would have distributed these amounts in a different way. And that's something you don't want. So fortunately, Marek Kaminsky looked at this problem also, and he introduced something called hydraulic rationing. And hydraulic rationing is like rationing with fluids. And this makes life easy. So life may be easier if you have a drink occasionally, but life is also easy if you make your problems a bit more fluid. You just need the right shape cup. So most of you will understand like what's communicating vessels. So you probably had a course in physics a long time ago. So communicating vessels are vessels that are connected by small pipes like you see here at the bottom. And I also assume that these pipes that connect the bottom parts and top parts are very, very small, but fluid would pass through, okay? And there's a law in physics that says if you pour in a fluid in any vessel of this, then the level of the fluid will arrive at exactly the same height in all vessels simultaneously. So let's suppose we have vessels where the vessel on the left has a total volume of 100, 50 on top, 50 at the bottom. The second vessel has a volume of 200, 100 on top, 100 at the bottom. And the third vessel has a volume of 150, 300, 150 on top and 150 at the bottom. And now let's see what happens if you pour in 100 units of fluid, 33 and a third in each vessel. If you have 200 units of fluid, it's 50, 75, 75. If you have 300 units of fluid, it's 50, 100, 150. You can just tell each of the widows, take your vessel and go home. It's consistent. Why? Well, because if you would look at a two-player problem with this shaped vessels, you get exactly the solution of the two-player problem. It's consistent because if we only have two vessels and the third vessel is gone, the amount of fluid would still level up to the same height. So nothing changes if you take out one of these vessels. If we want to solve the problem with 400 units, we find these numbers. And I leave it to you to check that if you look at only the first two ladies, they split 175 exactly as 50, 125, considering their claims of 100 and 200. If you look at the first one and the third one, they split 275 exactly as 50, 270, 225, considering their claims of 100 and 300. And if you look at the third pair of the second and third woman, they split 350 exactly as 125, 225, given their claims of 200 and 300, and keeping in mind this contested garment. 4 widows, well, no big deal. You just add 1 more vessel. So solving some problems in mathematics is easier if you make a nice drawing than if you write lengthy equations. And that maybe also takes me to the end of my story tonight. So I'd like to give you a little bit of my story, how I connect to these people, and to also introduce you to some different areas of game theory that, well, we've seen sharing money, we've seen competition, strategic behavior, and I'd also like to take you 1 step further into evolution. So this is my story of how I connect to the work of John von Neumann, John Nash, Lloyd Shapley, and Paul Baumann in game theory. I wrote my PhD thesis in 1989 on a topic called stochastic games, which in a way extends the work of John von Neumann, John Nash, and Lloyd Shapley, because John von Neumann was looking at matrix games, and like 1 matrix, 1 number, 2 players only. John Nash was looking at non-zero-sum games, but it could be more than 2. And Lloyd Shapley, well, he did his work on cooperative games, he did his work on matching, but he also did work on stochastic games. And stochastic games are also an extension of the work of John von Neumann, where Shapley kind of said, well, playing just 1 matrix games, that's a bit boring. I want to play a different game every day. So Shapley considered the situation where you would have a collection of games. And in each of these games, so each of these games would be like a matrix. And if you play a row and your opponent plays a column, you get a payoff. But then there's also a transition probability that decides what game you're going to play tomorrow. So you know all the possible payoffs, you know all the possible transition probabilities, and you want to choose your actions in such a way that your overall payoff, playing through all this sequence of games, is going to be okay. So you don't want to choose actions that take you to a game where your payoffs are lousy. Now, Shapley was looking into those games also as part of his PhD thesis in 1953 from a zero-sum perspective. What I did is looking at those games from a non-zero-sum perspective. So I was looking at equilibrium problems in stochastic games, where it was an open problem those days. And to be honest, it's still an open problem. So hardly anything is known if the number of players is more than 2. But I did make quite a number of steps. And these steps got me introduced or invited to work with Lloyd Shapley in UCLA right after my thesis in 1989. Then I was also invited to work at the Hebrew University of Jerusalem at the Institute for Advanced Studies. And accidentally, they had a year on evolution and game theory. And I found myself suddenly introduced in thinking about games that are not played, let's say, with pencil and paper, but going out into nature and observing how nature is playing games where species are competing with each other. And also in Jerusalem, I met with John Nash just a few years later. So this is how I got into nature in the early 90s, by working on the foraging behavior of bees and deciding on the policy that a bee would be using in deciding, shall I go to blue or shall I go to yellow? So it's decision problems for bees, where if you have a full group of bees that are all deciding their choices independently from each other, you would like them to go to the blue and yellow flowers in such a way that the food share or the food intake, no matter how it's distributed on the blue ones and the yellow ones, that it's distributed in a fair way among the bees. The bees want to optimize their intake. How does nature organize this? And what kind of capacity does the bee need to get the job done? So this got me into working on bees and flowers and spending my days not with pencil and paper, but sitting in the field and watching bees move from one flower to another. It led to studies on sex allocation in plants, to pollinator visitation across plants, to studies on parasitoid wasps, where every wasp mother can decide, and that's also a funny story, but every wasp mother, so for this specific type of wasps, the wasp mother can decide on every egg that she lays, she can decide, am I going to make boys today or am I going to make girls? Now, today, well, of course, there's a lot of genetic knowledge these days, but for humans, this is still quite technical and quite difficult. But these very tiny, small wasps, adult are only 2 millimeters big. They can make a choice like that. But wait a minute, if they can make a choice like that, how do we get natural equilibrium? You need males and females to get it done somehow. So we try to figure out what's the decision process inside this 2 millimeter female wasps. And we did so by running all kind of competition models using something called evolutionary simulation. So it's decision making in nature, basically. Well, this led to a number of workshops, first on biology in general, and gradually we shifted our work towards applications of this type of game theory, evolutionary game theory, on cells. So it's evolutionary game theory because the strategies evolve from one generation to the next generation. So the most successful strategies are the ones that you are going to see most in nature. So this is like trying to understand Darwinian selection mechanisms. And these mechanisms are visible in plants, in animals, in insects, but also in cells. So our latest studies centered largely on understanding how cancers develop in humans. So how does a tumor grow? Of course, there's knowledge by oncologists on how cells behave, but little is actually known about how cells develop, how the interior of a cell, or how tumors develop, how the interior of a tumor looks like. Of course, you can take out a tumor of someone who's sick, but once you open the tumor, it dies. So you can't see how it continues to grow or how it grows from early stage. So we're trying to understand how tumors develop, and we're trying to understand the mechanisms that or the processes that start developing as soon as you treat a patient with a medicine that affects maybe one type of cells, but not all types of cells. And we're collaborating on this also with a number of oncologists from a cancer center in Florida. And this led to, these studies led to multiple PhD theses. I think in all of these theses, the cancer topic is appearing somewhere. And my colleague, these were studies done with my colleagues Ralf Peters and Katrina Stankova, and of course with the PhD students Li Yu, Katrina Schneider, and Katrina Schuler, sorry, she's now called Schneider, and Jessica Cunningham. And Katrina Stankova was also one of the driving forces there. And she recently, last year, I think it was last year, she was awarded, no, it's the end of 2020, she was awarded an NWO Stairway to Impact Prize because of, let's say, shaking up studies on cancer by coming up with original approaches towards treatment. And by this, I'd like to end let's say my story, because also is 1.5 hours have gone. If you'd like to have some further reading and don't want to spend too much money, here's some nice and easy books. A very short introduction by Ken Binmore, and a graphic introduction to game theory by the Pastine couple. And if you read Dutch, you can also read my little booklet where most of these topics are also visible. So that's it for now.
So now we're going to welcome Noor, who's going to read out the questions. She's our operator of this lecture series, and since she's going to be present all the 5 lectures, she'll be taking care of the questions. And I'm turning myself off, or my camera off again. If the sound of Noor is not that well, because we had some problem at the beginning, then I will take over. Noor, the floor is yours, and of course, Frank.
Thank you very much. Hi, everybody. So my name is Noor. I was here from the beginning. I saw you posted a lot of questions. And first of all, thank you, Frank, for this very interesting lecture. I think we all learned about a lot of very useful and interesting theories. And we got a lot of tips for maybe rethinking our game theory at this moment. So let me take a look at the questions. One is from Hagar Tal. He asked a question, can game theory and free will be linked in some way? Has someone already done it? And if yes, who did and what was the link? So maybe...
Okay, so, well, maybe the first thing to say is that in these non-cooperative games that I started from, so the ones addressed by John von Neumann and John Nash, the assumption is that the numbers are simply given in some matrix or in some shape. So also in these games that Shapley examined, where you'd have a collection of games, all numbers are given, and actually there's no bound to what the player can do. So all players are free to decide on what to do. And so in that sense, they are completely free to decide whatever strategy they like. And that's also a little bit what you see in these Prisoner's Dilemma games that I direct you to in the PDF for you to look at later at home. So it's about, let me give away a little bit of what it's about. So it's about 2 players having to say whether they want to split the money or not split the money. If they both agree on splitting the money, they both get half. If one of them does not want to split but wants to cheat, the one who cheats gets everything, which means the players are completely free to choose what they want, and there's no law that's keeping them or that's saying you're not allowed to cheat. So there's a lot of free will. Of course, because I also saw there was a question relating to population development. if we look into evolutionary games, if you look into evolutionary games, the assumption is that children behave in the same way as what the parents do. So where's the free will? Change in behavior only arrives by mutation. Basically, mutation could say, well, maybe you get a larger tail, or maybe suddenly we start having people with orange eyes, and suddenly orange is very sexy. Well, then suddenly there's much more people living in the world with orange eyes. If that's a treat that's doing it good, and that's also transmitted to next generations. So in that extreme, like if we're trying to understand what's happening to world population, we would always assume certain traits of behavior. If we want to understand bacteria population, we try to go to people who understand bacteria. We try to make simulation models of how they behave and what happens if they reproduce. And then you see reproduction in numbers, and then there's no free choice. But in all the non-cooperative games that I was talking initially, of course, everyone is free to choose whatever they want to choose. But I'm not sure whether that's really what you have in mind. So
I hope we could answer your question. I think it was pretty clear. If it's not, you can always write it in the chat as well.
so maybe also like in the cooperative games that we saw that were about fairness principles of how to divide, the assumption is that there's a book of law, like the Talmud, and the book of law says, well, this is your problem, this is how you do it. You can like it or you can dislike it, but the judge simply tells you this is what you get. There's no strategy, and no free will in a way, right?
Okay, then I think we can go to a question of Angela Habibi. She asked the question, is everything in nature explainable with math? How do you know that something that happens in nature is not random, but follows a mathematical explanation? And are we biased as rational humans trying to find a logical explanation to every natural event?
Well, that's of course a very difficult and philosophical question. I mean, in the past 10 years, we've been working, as I've showed you, I've been working on trying to understand principles in biology and trying to understand principles that happen in cancer, not by saying this is how it works. So, for example, when we were thinking about how do bees make their choice of what flower type do I go to, it's just a theory that explains how the behavior could be like. It doesn't say that that's what's actually happening. But by playing around with these ideas or these, let's say, heuristic that would give good motivation of why would it make sense and why could things develop the way they do, or how could it go, we can run simulations that show what would happen if. Of course, you always need to understand that a model is not the same thing as the real thing. But like if you're talking about epidemic spreading, the model can help generate predictions what may happen. And that's also like in the cancer studies. So if you're treating a patient like this, what may happen is that the patient dies because of your treatment. If you're using a different treatment, maybe chances are higher that, well, maybe the disease is not going away, but it may be that the patient lives longer. Okay, and so currently in US, there's a group of oncologists that's experimenting with cancer patients that are kind of completely gone through all traditional therapy, And we're kind of given up, like, well, you only have a few months to live. But by now trying to generate models where you kind of offer, let's say, solutions where maybe the cancer is not disappearing, and they already have too many tumors, but you may try to find a way to make their life easy and more let's say, more human, and extend their life horizon for a longer time. And models help in doing these things. And so it's not that also a game theory model where, I mean, I have completely no history on cancer oncology. So I can make models, I can make numbers, I can use numbers, I can have guesses on what would make sense. But in the end, I need oncologists to tell me, use these numbers, or to tell me, well, what you tried out there, that's completely ridiculous. That doesn't make any sense at all. Why don't you try this? Or can you also incorporate that? And I think this dialogue is very important, because like, for example, if it comes to treatment, so usually if a patient is being treated, you say, well, we have so much dose. We're just going to split these dose in so many sessions. We do equal amount in all sessions. As a mathematician, I would say, well, why don't you start with a higher dose and gradually go down? Or why don't you make the time intervals between the doses depending on the response of the patient? Well, all these things are often not considered because there's just a standard way of doing things. And there could be, maybe a lot could be gained if you include strategy in there. And gradually, also because of the data that's becoming more and more available, people are starting to include all kind of principles of strategy going on into these things. And I think that's beneficial to get the dialogue going, rather than having each one working only in their separate domains. Like, I didn't learn anything of oncology in my studies, but I'm sure the oncologists won't learn anything about strategic game theory in their studies. Not yet. Maybe in the future they do.
Thank you very much. I think it's also a very interesting part to look at it and combine, like, especially the communication and the usage of that also in medicine.
One second, there's someone at my door.
Oh.
I guess it's the guard of the building saying, you have to leave, we're closing. No. They will wait. Another 15 minutes, please. We have some questions.
I'm back.
Okay.
Yeah.
Very nice.
Security in the building, sorry.
Oh, we already thought so.
Yeah, they're half an hour too early, so
Okay.
okay, I'm back.
Okay, we also have another question from Rachel Nilwick.
Okay.
Wondered, is there a way this principle on cooperative play when you can't really determine, oh, it slipped away.
Yeah, I saw the question. What if you don't have all the information? Like for the cooperative game, you would like to have, for each subset of players, you would like to have a number. Very often those numbers are not available. And even if you would have all numbers available, calculating something like this Shapley value would be a highly complex task. And the calculation would run into complexity problem and your computer would get stuck. So what's happening in reality is that you make estimates, and especially if there's a large group, like also in auctions or things like that that are happening in online trading, there are very many different parties, but there's also assumptions that many parties are kind of behaving in the same way. So they're not all really too different from each other. So all these things can be done and will be done but I don't know too much about all these different fields. So when I started in these fields and went to the first, let's say, big conference, there were around 120 people. When we had the meeting in Maastricht here, there were nearly 900 people. And I'm sure that the number of people working on these things is at least double this amount. So the field is is growing very fast. It's growing in very many different directions, and it's almost impossible to follow all these directions. But yes, there are many ways around it, many ways that are looking also at Shapley values where only very specific orders are taken into account.
Yeah, I also think that it's getting like very prominent, and also more and more the more data we have. There's also a really interesting question that got upvoted, also about the recent discovery of Bitcoin from Frederica Camarata. She's wondering, is there a way to implement game theory for the development of a fair economic system? Would Bitcoin be a good point to start from, since there's a finite amount of it and cannot be printed at infinitum like our current currency?
It's an interesting question, but I fear that Bitcoin is running into all kind of electricity problems, and it's not the way to save the world in a way. And yeah, if it's about can you, yeah, so that's another difficult thing is, of course, can you use game theory to stimulate more fairness? In most game theory models, you assume that every player wants to get the best he can get, or the best she can get. That's an assumption. And why is that? Well, I think that when you were at school, well, you were trained to calculate, for example, solution, find the maximum of a certain graph. Usually, if people want to maximize their gains in the profit, they don't say, well, make sure that my profit is at least this much, then I'm happy. So somehow human is always triggered to get more. So there's greed in a way included in the model. Why? Well, because maximizing something is easier than saying, okay, as long as the solution is somewhere in there, I'm happy. That's somehow more difficult to model also. So this principle of wanting to get the most out of it, that's also what's called rationality in game theory. And it's one of the driving principles of how you arrive at solutions. Now, some people have also studied what happens if players are not doing always the rational thing. Now, not rational thing, I don't mean that sometimes you're doing things because you like your opponent and you want to help them, because we assume that the numbers already include whatever feeling you may have towards what's happening to someone else. So if you can get 0 and your opponent gets 100, or you can get 0 and your opponent gets -100. So if it's a one player decision problem, you can decide either getting 0 and give your opponent 100, or getting 0 and give your opponent -100. I know in class, all students say, well, of course you choose the one where your opponent gets 100. Well, we assume that if there's a 0 written for you in both cases, you're really indifferent. Why is that? Well, that's why there's a 0. If you prefer one more than the other, there should be a different number. So we try to understand what's happening if the number really explains how much you get. And any of these, let's say, social interactions are already taken into account in the number that you're seeing. And even then, but irrationality, can sometimes be included as like that players make mistakes with small probabilities. They try to choose one action, but with some probability they take the wrong one. So you try to incorporate some flexibility there in what they're doing. And this leads to, of course, different outcomes. But I'm not sure whether that was really the question.
Yeah, thank you very much. If you still have some questions, you can put it in the chat as well. And we have one question that I think also suits very well from an anonymous comment. He asks if game theory and free will can indeed be linked, taking into consideration that participants of game theory expect a win. May we assume that there is no true altruistic act in humanity?
Yeah, well, also regarding altruism, there's all kind of algorithms regarding with respect to altruism. It's happening also. So altruism is not always what you expect immediately on the first sight. So, for example, I'm trying to find the name of a certain animal. Can make it up now. Stokpaardjes. What's the name?
I was thinking about maybe Europe stokpaardjes.
Can't find the name right now. Sorry, but there's for example also you know some animals they live in groups, social groups, and one animal would go on guard when the rest are eating. You see that, for example, also in goose or geese. So if you see them sitting in the land, there's always a few that are not eating, they're just watching. They're trying to see if there's predators around. Now, there have been experiments that show that, well, of course, if there's a predator around, the one who's on guard has to warn, has to shout, "Oh, go, fly." Well, experiments show that if the animals that are close by are family, then the one on guard is willing to warn them. If the ones nearby are not family, they will just not say anything, because by shouting you risk that you are the first one being eaten, because you pull all attention to yourself. But it shows that some animals are willing to risk their life if they can help family members escape. Now you can say, well, is that altruism? Well, maybe not completely, because by risking your family members, you're allowing your genes to continue into next generations. So there may be a personal benefit after all. So it shows like altruistic. Why would I help someone? Why do people run into burning houses?
Got some help in the chat as well. So
Okay.
on the stokpaardje, we got some advice. It could be a meerkat or a hobby horse.
A meerkat, yes, of course. Sorry. Yeah, very good. Very good. Yeah. But so very often there's a bit more to the story. But it's definitely interesting analysis. But to be honest, like for example, in one of the PhD theses that I showed, we also did a study on, for example, stimulating countries to get more clean air, to have a more sustainable, good environment. Right now, everyone's just polluting. How to stimulate clean policy? Well, maybe by imitation, but if it's just imitation, if you somehow need fines to get it operational. So if you want Europe to have clean air, you need all these countries to start cooperating and do something and maybe benefit, because if one country alone is trying to do something, it's never going to work. So Netherlands can do a lot on trying to invest in all kind of clean energy, but if Germany, Belgium, and France and all countries around us are not doing anything, it's not going to improve the climate here over the Netherlands. So you can play around with these models, like what happens if we assume that, well, with some chance, people are going to follow nice examples, with some chance they don't. So of course you can incorporate all kind of prices, and you can try to understand a little bit like what could happen if, and maybe you conclude, well, we do need some external force to get it operational. Also, like we're all driving motorways maybe, and are confronted with traffic jams. So increasing pricing on certain routes helps reduce traffic jams, because it spreads the traffic over other routes. That so you take away some of the pressure on the popular routes. So all these things are possibilities for experimenting with in all kind of simulation models before you really decide on let's do this or that in real life. So I'm a big fan of trying to predict what will happen if, and sometimes simulation models can give you a really good grip on problems that maybe are too complex to really solve by writing a system of equations. Because the things that you can really solve are quite limited.
So I think we have time for our last question.
Yeah.
Maybe from Rolf Sneders. Can game theory predict any future regarding the devastating effect on human population explosion on Earth? Maybe that's also something interesting for the finish.
Well, I'm not sure whether I'll like. There's the book by Dan Brown. I think it's Inferno. It's currently, it has just been positioned in Netflix. It's addressing world population issue, and if you read the book Inferno, so on one of the first pages, it says it's about a game theorist who's writing simulations to understand what's happening to Earth. But it wasn't me. So yes, you can also model that type of thing and try to understand what will happen. And that's also like you hear in the news nearly every day these days this R number. So I think there are many ways of trying to understand how does this work, and how does this R number, well, it's a very blunt, of course, parameter, just one parameter, and of course in reality it's also about how people are connected. Like, for example, if we're talking about diseases spreading, like food diseases spreading, there's a lot of things that are kind of connected to the pathways that we're using, the airports, the harbors, the road networks. So these are kind of lines where things are passing through, and very often those lines are not yet included in all the analysis. And I think it's very important that those things are done. And for example, of course, now we have all these different policies in different nations. People are crossing borders, so it would be better if there's a synchronization of behavior across the border, and not just everyone doing what's good on their own, and in border regions people are playing whatever happens on what side of the border. So I think, yeah, you can model a lot of things, and you will maybe get some better ideas of what's happening, but it doesn't immediately offer you a solution. But you can try out all kind of ideas in a safe way without playing with real lives and real humans. And I guess that's what pops up in my mind at the moment.
Thank you. It is indeed time, so I'm very sorry that we didn't get to the last 3 questions.
Well,
maybe if they're very important, you can always send a mail, I guess, to Frank.
yeah, you're
Thuijsman.
welcome to drop me a mail.
And you can find him back at, if you Google on Maastricht University, Frank Thuijsman. I'm sure you'll find his email. Otherwise, you can send it to Studium Generale. I want to point out to everyone that we have an interesting lecture coming up about consciousness and the brain, especially also those for people who are interested in artificial intelligence. It's also part of this lecture where we see if artificial intelligence is indeed possible, and then what that has to do with consciousness. That's on Monday. Look on our website of Studium Generale if you're interested in free lecture. Just zoom in, I would say, or log into Zoom and see what that's about. And otherwise, I see you back next week. In the chat, there's already some nice remarks that we can find back about the lecture that was very interesting. Okay. So we keep that open for a minute or two.
Wonderful.
Thank you, and see you next week. Thank you also, Noor.
Thank you very much. You're welcome.
Thank you for organizing, and thank you all for attending. Bye-bye.
Bye-bye. Thanks.
Dag Noor. Wat